Okay, so now we're going to officially get our next unit started. And so for this entire unit, we're going to study Trimly Iron a Regretting Goth. That can't be right. What are we really studying? No way, you're kidding me? There's more right triangle trigonometry we're able to study? We haven't studied all of it already? That's fantastic. So we're going to... Why are there 6 aliens? That makes no sense. We're going to study right triangle trigonometry. Get those aliens out of here. So, for the first lesson, we will be able to solve right triangles. Now, you're probably wondering, what on earth does it mean to solve a triangle? Well, each triangle, of course, has 3 pieces. There are 3 angles, and there are 3 sides. So it might have been nice if we had an illustration that showed those 6 pieces. I don't know what happened. And if I give you 3 of the 6 pieces, most of the time, boy, what it is, most of the time, we can find the other 3. All right. Now, if one of the pieces happens to be a right angle, our task is greatly simplified. If we don't have a right angle, the task is more complicated, but still possible. For this lesson, however, every triangle will have a right angle. And that, of course, is why the learning target is solving a right triangle. Every triangle will have a 90-degree angle. Okay, so to solve a right triangle, I'm going to give you 3 pieces. You're going to find the other 3 pieces. So in this first example, we know angle A is 36 degrees. We know angle C is 90 degrees. And we know side B is 8.2. We need to find angle B, side A, and side C. And while we're doing this, we're going to need to show a lot of step-by-step work. So the first piece of work I should show is, I don't even know where to start. What should I do first? That's right. It's time to paint a picture. Or if we're not fantastic artists, perhaps just drawing a triangle with it. Now, other than trying to make one of the angles look like it's a right angle, I'm not going for artistic perfection. I should label everything I know, so I'm going to label those angles A, B, and C. Of course, angle A I know is 36 degrees. Angle C, I put a little mark so I know it's 90 degrees. And of course, side B needs to be across from angle B, so that's where we're going to put the 8.2. Okay, so now that I got a picture to look at, what should be the very first thing I actually try to find? Well, I think the easiest thing is going to be angle B. Because it's a triangle, I know the 3 angles must add up to be 180. So by doing a little bit of math, my friend the calculator will tell me that 36 plus 90 is 126. Notice I actually write that on paper, however. And using the calculator, I can figure out that 180 subtract 126 is 54. But again, I still want to show at least some work on paper. Right? If you don't want to show the minus 126 on each side because you're like, hey, we've done enough of that kind of algebra already, fine, but you got to show that, hey, the original setup is you're adding the 3 angles together. You figured out that 36 and 90 combine to be 126. And then, of course, the difference has to be 54. Well, let's add that to our picture. Let's put the 54 degrees in the right spot. And I'm going to also add it in with my original list there. So I'm going to put that 54 degrees in. I'm like, now I've got to find either side A, which happens to be a leg, or side C, which happens to be the hypotenuse. Well, thank goodness we just studied some trigonometry. If I hang out at the 36-degree angle, I now know which side is opposite, which side is adjacent, and which side is the hypotenuse. Now, if you just want to put like OPP for opposite and ADJ for adjacent and HYP for hypotenuse, right? Abbreviate them a little bit. Don't just put one letter though, because if you just put O for opposite, you're going to start to wonder, hey, is that side O? Or if you just put A for adjacent, you're going to get really confused on which side is side A. So if you're going to abbreviate, don't just put one letter. I recommend 3 letters, right? I usually use OPP if I abbreviate opposite, ADJ for adjacent, HYP for hypotenuse. Well, if I know the adjacent side, tangent's probably going to be the easiest one to work with, because tangent is opposite over adjacent. And so tangent of angle theta, boy, did we talk about that last unit? Mathematicians usually use the variable x when we're solving an equation, but in trigonometry, when we're solving for an angle, we often use theta. And I bet last unit I used tangent of A with you folks, but I just put theta. I just realized that. Theta is kind of like a variable for whatever angle we need to use. But if I'm looking at angle A, I'll substitute 36 degrees in for angle A. Opposite side, of course, is lowercase a. Adjacent, of course, is 8.2. I need to multiply each side by 8.2 to isolate the variable A. Now, of course, I'm going to grab a calculator, make sure I'm set in degrees, and I'll do 8.2 times tangent of 36. If the directions don't state how to round off, I'm kind of free to choose wherever I want. I usually pick the nearest tenth. So I'll say, okay, side A is about 6.0. I can add that to my picture. I can also add it over to my original list of all the pieces. Now, because it's a right triangle, if I'm missing just one side, the Pythagorean theorem is probably my quickest, easiest route. Now, if I'm using a calculator, I normally have that previous answer already in there. If you just use the 6.0, that would be fine. But because I had the previous answer already on the calculator, I just took the previous answer, squared it, grabbed the 8.2, squared it. And of course, the calculator does all the work for me, but I still show on paper that I understand I have to square side A, I have to square side B, I have to add them together, and then I have to take the square root. Comes out to be about 10.1. So that's my hypotenuse, and I can also add it to my answer display. Right? But I'm not just putting the answers down. I'm showing the equations that lead up to the buttons that I push on the calculator. Right? If I'm going to add the 3 angles together to make it be 180, I'm going to show that on paper. If I'm going to use tangent as opposite over adjacent, I'm going to show that on paper. I'm going to show that, hey, I'm doing tangent of 36 degrees equals side A over 8.2. And I understand that to get A all by itself, I got to multiply by 8.2. If I'm going to use the Pythagorean theorem, I'm going to show the steps on paper. Okay, once again, we'll skip the Bob Ross joke and just get that triangle up there. I know side A is 3. I know side C is 7. And instead of putting 90 degrees on there, I just put the little mark so you know it's a right angle. How on earth am I going to figure out angle A? Well, opposite is 3. Adjacent, got no clue. Hypotenuse is 7. Well, if I know opposite and hypotenuse, I know sine of any angle is opposite over hypotenuse. So here, sine of theta is opposite over hypotenuse, or as I probably worked with you last unit, sine of angle A would be opposite over hypotenuse. All right, so angle A, which is the angle we're actually trying to find, the opposite side indeed is 3. The hypotenuse indeed is 7. Wait a minute here, that's sine of angle A. I don't want the sine of angle A, I just want angle A. What am I going to do? That's right, we have to do the inverse sine function. If I actually want the value of A, I have to do the inverse sine function for 3/7. Again, on my calculator, I make sure I'm in degrees. I make sure I'm using inverse sine. Notice I use parentheses to make sure that 3/7 is the value. If I don't use parentheses, the calculator is going to think I want the inverse sine of just the plain old number 3. And then after I do that, divide that by 7. And that would create a really bizarre result on the calculator. Right? I got to make sure it understands that, hey, I want to do 3 divided by 7. And whatever that value is, take the inverse sine. Comes out to be about 25.4 degrees. Again, I rounded to 1 decimal. I can add it to my picture. I can add it to my number display. Of course, I know 2 angles. Easiest way to find that third angle, I know they've got to add up to 180. And again, even though I'm going to use a calculator, I still show on paper that I understand those 3 angles have to add up to 180. I use the calculator to add 2 numbers together. I use the calculator to do some subtraction, but on paper I'm showing I understand where that 64.6 degrees came from. Add it to my picture, add it to my number display. Of course, with a right triangle, the beauty of knowing 2 sides is the Pythagorean theorem will always get us the third side. And this one might be all mental math, right? You know 3 times 3 is 9. You know 7 times 7 is 49. You can probably do 49 subtracted by 9 is 40 in your head. But notice I'm still showing each step on paper. Now this is where it gets real interesting, because usually with square root of 40, you would just simplify it. But mathematicians, when they're solving right triangles, for whatever reason, instead of leaving it as 2 root 10, they actually want us to take that square root of 40 and turn it into a decimal. And so we'll say about 6.3. Right? In pure math, we usually would leave it as 2 root 10. But solving right triangles, we're kind of on the verge of applied mathematics. Right? You'll see this happen quite often in physics, where you've got different triangles you're working with. Trust me, that SOHCAHTOA gets used so often in physics. And when you're in the applied maths, like chemistry or physics, the chemists and the physicists, they usually want decimal equivalents, right? It's like round off to the correct amount. In fact, in physics, you'll even study sig fig, significant figures, right? Before you even start a problem, the directions won't tell you what decimal point to round off to. You'll have to figure out how many significant figures should I include? At what decimal point should I round off to? That's actually a lesson early in physics. Now, the nice thing about having a right triangle is, well, with any triangle, you can always use the fact that the sum of the 3 angles have to be 180 degrees. because it's a right triangle, we could almost, of course, use the Pythagorean theorem. And because it's a right triangle, we can also use our good friend SOHCAHTOA. Alright, if it's not a right triangle, I can't use the Pythagorean theorem. If it's not a right triangle, I can't use SOHCAHTOA. And then, of course, if we are allowed to use SOHCAHTOA because it's a right triangle, we can also use the inverse functions. So that's a lot of powerful information, right? Being a triangle lets us add up to 180. But being a right triangle opens up the Pythagorean theorem, and it opens up SOHCAHTOA. There are very few questions on the worksheet today. So the expectation, of course, is that you're going to show some beautiful step-by-step work on that worksheet. And then with IXL, some extra practice on working with those trig ratios.